Okay,
You know,
our local organiser Peter is going to speak now. Binary submatrix. Thanks, Peter.
Alright, hello everyone.
sorry.
Yeah, I'm very happy to be here, and thank you for everyone that's given talks so far, and people that will give talks tomorrow, and of course thank you to Henry again for having us here. So the aim of this talk is to get you interested or excited about problems in Matroid theory to do with representable Matroids that are inspired by problems in graph theory. Now that's obviously nothing new, but I would contend that a lot of the really interesting stuff in recent Matroid theory has come from graph theory problems that are in the world of minors. So the natural partial ordering of minors and things like Rota's conjecture, splitter theorems and so on. Of course we care about deletion and contraction, and unfortunately for everyone, connectivity comes up naturally as part of that. So the problems I'll be talking about are from problems from a different part of graph theory. Really the world of subgraphs, things like chromatic number and clique number and so on. So I think that, I mean, you've seen me talk about some of the stuff at Princeton, but I'd just like to give a survey of some questions that I find interesting and things that we know already. Okay, so I'll start with a classical theorem. Turan proved this in 1941, and it just answers a simple question. I've got a graph, and I say it's got no KT, it's got no complete T-vertex graph as a subgraph. How many edges can it have if it's got n vertices? And Turan showed that the answer is it can have at most 1 minus 1 over T minus 1 times n choose 2 edges. Now, this isn't actually exact for every n. It only holds with equality that's bound when n is a multiple of T minus 1. And the reason is because it holds with equality for what are known as Turan graphs or balanced complete multipartite subgraphs, complete multipartite graphs. So this is a picture here of the densest graph on n vertices when n is a multiple of 3, so that the graph has no k4. So you want this complete multipartite graph with the parts as equal as possible. If n is not a multiple of 4 in this case, then you'd have two parts differing by at most 1, and you get the bound that's slightly less than that. But for our purposes, we'll just think of this 1 minus 1 over T minus 1 as kind of the maximum density you get. The proof of this is not very difficult. You show that if you have a KT-free graph and it's not a complete multipartite graph, then you can tweak things in the neighborhood of 3 vertices and improve things. And then if it's not balanced, you should probably make it more balanced, and that will improve things. So that's the whole proof, really. So the analog between graphs and matroids that I'll be talking about constantly, it maps Turan's theorem to what's called the Bose-Burton theorem. This was proved in, I'm blanking on the year, I think it's 1966. It was in the 60s, and it was in the inaugural issue of the Journal of Combinatorial Theory, I just learned this morning. And this answers the analogous question for matroids, which is I've got a simple GFQ representable matroid, and I tell you it doesn't have a rank T projective geometry over GFQ as a restriction. Now I use the word submatroid in the title. I'm using the word submatroid to hopefully evocatively make an analogy of subgraphs. I will probably alternate between saying that and restriction, but I think submatroid is a word that feels right in this setting as well as restriction. So this theorem says that if you don't have a rank T projective geometry as a restriction, then you have at most 1 minus 1 over q to the T minus 1 times q to the rank number of elements. So q to the rank isn't quite the number of elements in the rank R projective geometry, but it almost is. So this thing in front of it is really a density. So if you have no rank T projective geometry restriction over GFQ, then your density is at most 1 minus 1 over q to the T minus 1. Now this does actually hold with equality for all T, and it's because exponential things behave better with respect to divisibility. The objects for which this holds with equality I'll call the Bose-Burton geometries, and they're very simple. To get a Bose-Burton geometry of rank R, and I would say the order is T, I take a rank R projective geometry and I throw away a rank R minus T flat. So I throw away a codimension T subspace, and that's a Bose-Burton geometry. And that's kind of, it's completely analogous to a complete multi-part graph. If I do this for t equals 1, I'm throwing away a hyperplane and I'll get an affine geometry. And if you think about the binary case, then an affine geometry is kind of a canonical large triangle-free matroid in exactly the same way that a complete bipartite graph is a canonical large triangle-free graph. So these Bose-Burton geometries give you the densest things that don't have some projective geometry as a submatroid. Now, I said Turan's theorem is fairly easy to prove. The proof's in the Wikipedia article. This is way easier to prove. If you want to prove it, so the proof for binary matroids with no triangle, all I do is I say I'm going to take a point in my matroid. Now the rest of the matroid partitions into lines that contain that point, well, lines of the ambient space that contain that point. So if my matroid has no triangle, then it can only contain at most one point from each of the lines. And so I can really only have about half the points. And in general, you just start with a projective geometry which inductively exists of one less rank than the one you're looking for, and then say all the ways I could try to extend it to a larger projective geometry, none of them can work, so I must be missing a point from each of them. And it's really a completely trivial counting argument. And the reason is because the projective geometries have so much more symmetry than cliques. Any 2 points in a projective geometry are the same as any pair of other points, but any 2 edges in a clique, they could be incident or non-incident, so there's less symmetry in a clique. And this is something that happens surprisingly often. I mean, usually matroids are horrible and they're worse than graphs, but there's many instances in this setting where matroids are actually quite a bit nicer. So something that goes with these extremal questions in graph theory is chromatic number. Of course, the Turan graphs are kind of the biggest graphs of a certain chromatic number. And we know that the chromatic number of a graph is the smallest number of colors you need to properly color the graph. With no 2 adjacent vertices getting the same color. And a slightly obtuse way to state that is that the chromatic number of a graph is the smallest t, so that the graph is a subgraph of some complete t-partite graph. Now I'm defining it that way because it's analogous to the to a parameter for matroids. So I'm going to call this the critical number. Of course, as James Oxley could tell you, this was defined as the critical exponent by Crapo and Groda in 1967. So I'm very happy to be talking about it here. The critical number of a matroid, it's easiest to define if you think of this matroid as a restriction of a fixed projective geometry. And it doesn't have to be a spanning restriction, but it might as well be. So I have a matroid. It's a restriction of a rank R projective geometry over GFQ. And I ask, what's the biggest flat of the projective geometry G that I can find that's completely disjoint from the ground set of my matroid? And the critical number of my matroid is the codimension of that flat. So if that flat has rank R minus T, then the critical number of my matroid is T. Now equivalently, and this is analogous to the definition I gave of chromatic number for graphs, it's the smallest t so that your matroid, sorry, that should say m, the second one, such that m is a restriction. It's the smallest t so that m lives inside a Bose-Burton geometry of order t. And it really doesn't matter if the Bose-Burton geometry has higher rank. There's sort of the higher rank and the codimension in the definition cancel each other out. So you can think of it. This is independent of the choice of G and the rank of G. Alright, so there's some natural questions you can ask. Critical number behaves nicely with graphic matroids. You don't actually need the chi of G is greater than 1 in the statement, it's true anyway. If I have a graphic matroid of a graph G, then the critical number of the associated matroid is the base Q logarithm of the chromatic number of the graph. Now, implicit here is the fact that when I talk about this chi of m, the critical number of m, I'm suppressing the Q. So if I'm really thinking about a graphic matroid, then I could be representing it over any number of fields. The critical number of that matroid with respect to different fields would actually be different. So the ternary critical number of a matroid could be different from the binary critical number. But for most of this talk, I'll be just talking about GF2 anyway, and hopefully it should be clear from context. So the critical number of a graphic matroid is the logarithm of the rounded up logarithm of the critical number of the graph. A graph with critical number 1 is something that lives inside an order 1 Bose-Burton geometry, which is an affine geometry. So that's just the same as being a restriction of an affine geometry. And that's the analog of being bipartite in the binary case. And also, there's this familiar theorem that a graph is bipartite if and only if it contains no odd cycles. This is also true for binary matroids. Alright, so Turan's theorem is, a fairly easy theorem. A much more interesting theorem in the same vein is the Erdős-Stone theorem. And I'm kind of presenting this simultaneously in both the graph and the matroidal setting. So I need a little bit of notation. I'm going to define this thing xhn or xnr, depending on whether I'm in graphs or in matroids. If h is a set of simple graphs, then xhn just denotes the largest number of edges you can have in a graph on n vertices that doesn't have any subgraph in that forbidden set. So Turan's theorem just says something about x, kt, n. And then analogously, if I have a set of simple GFQ representable, we could think binary matroids, then xnr is the maximum number of elements in a simple matroid representable over that field that doesn't have any of these forbidden submatroids. So these are really the same thing. I'll probably stop saying the word simple because everything in this talk is simple. I'm not going to be taking any minus, just submatroids. So I think just as you don't keep saying simple graph if you're doing graph theory, I won't talk about simple matroids. It will just be assumed. So here is just a restatement of Turan's theorem and the Bose-Burton theorem in this language. If you exclude a clique, you get 1 minus 1 over t minus 1, and then choose 2 edges at most, when n is a multiple of t minus 1, and the Bose-Burton theorem tells you what you get if you exclude a particular projective geometry. Okay, so the Erdős-Stone theorem, it tells you what you get, well, it almost tells you what you get for excluding an arbitrary subgraph. So it says if I exclude a subgraph H, one way to get a big graph with no H is I take a complete multipartite graph of order 1 less than the chromatic number of H. So any restriction of a complete multipartite graph will be colorable with that number of colors, so H won't be a restriction of such a graph. The Erdős-Stone theorem says that you can't do any better than that up to a little O of 1, a little O of n squared term. So xhn, this thing here, is the size of this is the density of the complete multipartite graph of order 1 lower than the chromatic number of H. This says you can't do really much better while still being H-free. So this really, it tells you how big xhn is for arbitrary H to a lot of accuracy. So a few years ago, Jim Gillen and I, we proved a geometric analog of this, or matroidal analog, and it's almost exactly the same statement. It's just sort of an exponential version of it. It says that if I exclude a particular GFQ representable matroid as a submatroid, and I ask how dense you can be, then you can't do much better than taking the appropriate Bose-Burton geometry, and you can do a little bit, but not much better. So these theorems both apply to particular matroids, and you just exclude one thing. But if you're excluding a set of matroids or a set of graphs, and your set of graphs it contains at least one non-bipartite graph, or your set of matroids contains at least one non-affine matroid, then these theorems just trivially give you asymptotics for excluding your finite set, not just a single thing. So it's just really taking a maximum of the chromatic number of the things you're excluding, something to that effect. But this really fails to tell you something if you're only excluding a bipartite/affine object. If I exclude a bipartite graph, then this expression here is 0. So you actually still get a true statement. You get xhn is little o of 1 times n choose 2, but that's not asymptotics. That just tells you it's less than n choose 2, or it's vanishing compared to n choose 2. And similarly here, if you exclude an affine thing, you get 1 minus 1, so you get, again, little o of 1. So if this thing's non-zero, then this gives you asymptotics for xhn, but if it is 0, it doesn't give you asymptotics. It tells you something true, but not the asymptotic value of something. Okay, so this is the very interesting base case. So these are restatements of the two Edler-Stone theorems in the special case where you're excluding a bipartite thing or an affine thing. And you can see when you look at this that these are not, these are not the end of the story. In both the graph and the Matroid case, the base case is the most interesting part of the Edler-Stone theorem when you prove it. The same paper that proves the whole Edler-Stone theorem for graphs is the paper that does it for bipartite graphs also does it for all graphs, so that was done at the same time. For Matroids, the base case of the Edler-Stone theorem, the proof was written down by Bonin and Chin in 2000 for the binary case, but actually the base case is a hugely complicated statement for Q not equal to 2. It's equivalent to the geometric density Hales-Jewett theorem, which is a pretty big deal in Ramsey theory. It was originally proved by Furstenberg and Katznelson in 1980, and they proved it for all Q using these non-constructive ergodic theory techniques, and then subsequently combinatorial proofs have been published famously by the Polymath project.
So what makes it so much more difficult for Q greater than 3?
That's a very good question. I'm going to give you a bunch of points in space. I say find 2 collinear points. It's not very hard.
Yeah, I'm sure.
If I say find 3 collinear points, that's hard. That's essentially the problem. So the actual only interesting case is if you're just trying to find a rank 1 affine geometry, just finding a line. Once you can do that, you can sort of bootstrap your way up. And it's very hard to find a 3-point line in a dense set. It's very easy to find a 2-point line in a dense set. So that's the reason.
Okay, thank you.
So Bonin and Chin, they sort of did something exclusively in the setting of binary matroids, and I mean, really, it is part of something much bigger, but it's, I mean, this paper is sort of hard to look up. It's, of course, they don't talk about matroids in this paper that they wrote in 1980 using ergodic theory. Okay, so in the excluding a bipartite case, there's a lot of work. People like Jacques Verstraete have published huge numbers of papers on this. It's a very interesting question, how dense you can be while excluding some bipartite graph. And just a couple of weeks ago on the archive, there's a beautiful paper that resolves a conjecture about this. I think it's Boris Buch and David Conlon. They resolved a conjecture by showing that if I give you a rational number between 1 and 2, then there's a finite set of certainly bipartite graphs, so that if you exclude that set of graphs, you get an order of magnitude of n to that rational number as your extremal function. This used some very, very heavy-duty analytic techniques. The construction's not so difficult, but proving that it's correct is very difficult. I mean, this is a very recent paper. I recommend looking at it and telling me what half the stuff in it means. They also strengthened their conjecture. They found a finite set of graphs that conjecture you can just do it with 1, which would be pretty cool. So when you're dealing with this exponential matroidal version of this function, there are some more questions, because this is sort of a lot more restricted, little o of n squared compared to little o of q to the n. You can ask, could I exclude some stuff and get a polynomial growth rate function? I actually don't know. Could you get a polynomial value? You certainly can get exponential values. I believe that coding theory constructions give you an order of magnitude of something like root 2 to the r, and various things you can do. So this is sort of the best I could muster as some kind of analog of the conjecture that Buch and Conlon proved. I would conjecture that you can get 2 to the alpha r for any rational alpha between 0 and 1, but I wouldn't know how to prove this. But I think this would be a beautiful theorem if someone could. All right, so that's all for the Edler-Stone theorem for a while, well, for now. So the next couple of slides are on the stuff that I think probably all of you saw me talk about in Princeton. I just wanted to recap on some of it. Rutger will be talking about stuff in this area in a lot more detail after me. So this is the the graph theory versions of what I'm talking about is to do with the interplay between density and chromatic number in triangle-free graphs. So suppose I ask you for a triangle-free graph and I want it to have large chromatic number. I mean, that's easy. There's classical constructions for doing that. The class of triangle-free graphs is very rich. But if I ask you for a dense triangle-free graph, then it gets more difficult. The base case of Turan's theorem, which was proved by Mantel, I think more than 100 years ago, tells you the triangle-free graph is no bigger than a complete bipartite graph with balanced sides. And of course I could take, so that, I mean, that's fairly dense. That's got about half the possible edges. I can take any subgraph of that, and that's still going to be triangle-free. Now, if you define density as just the number of edges over as compared to the size of the clique, then it's pretty easy to construct slightly silly examples of dense triangle-free graphs, because what I could do is take a complete bipartite graph that uses nearly all the vertices and then put my favorite interesting triangle-free thing next to it as a different component. And that's almost as dense as this, but it's sort of only dense because it's got a big component that looks like that. So it turns out that the right question here is, instead of saying density is the number of edges over the number of vertices choose 2, you say it's actually the minimum degree over the number of vertices. Now when you define density that way, it's very hard to construct dense triangle-free graphs that don't just live inside here. One way to do it is to take a 5-cycle blown up like that. Now that gives you a density of 2/5. So the minimum degree of this thing is 2/5 n, and you can take any subgraph of that. And you can't do anything else above a certain density. As a result of Andras, Vacquerie, and Sosch, they showed that a triangle-free graph whose minimum degree is slightly too big to be this, bigger than 2/5 n, actually has to live inside here. Has to be bipartite. And a convenient way to say that in this setting is that it's homomorphic to a 2-edge graph. If you shrink both sides of the bipartite graph, then you get an adjacency preserving map to a 1-edge graph, 2-edge graph. And then Jean showed that if you're more dense than 10/29, then in fact you can only take a subgraph of one of these. There's nothing more you can do. So you're holomorphic to an edge or to a 5-cycle. Now this number 10/29 is, I mean, it's pretty close to a third. And so you could ask, how far down can these theorems go? I mean, something nice is true after 2/5, something nice is true after 10/29. So talking about lists of homomorphs as outcomes it's pretty hard to prove things once you go below 10/29, though not impossible. Sort of an approximation to a structured theorem that has an outcome like this is the property of having bounded chromatic number. Any graph that lives in there has chromatic number 2. Any graph that lives in there has chromatic number at most 3. So if you have a structure which is being homomorphic to some particular small graph, then it's sort of an approximation of that is just the statement that you have low chromatic number. So I'm going to talk about theorems whose outcome just says low chromatic number rather than the outcome saying being homomorphic to whatever small number of things. And some very nice work has been done on this. Carsten Thomason proved in 2002 that if I give you any density constant which is strictly greater than a third, then the triangle-free graphs above that density have bounded chromatic number. So the triangle-free graphs of density at least a third plus 1/1,000,000, they can't have arbitrarily large chromatic number. In fact, this result's been improved a lot. In fact, they're all full colorable, but that's neither here nor there for the purposes of what I'll be talking about. And then this was a really beautiful theorem because Hagquist showed a long time earlier that in fact if you have any fixed density strictly below a third, then you can beat that density, be triangle free, and have as large chromatic number as you like. So there's a complete threshold value of a third. Things really change from lack of structure to structure between somewhere below a third and somewhere above a third. So this is a very interesting behaviour, and this has been very well studied. Really, these results are the end of a very long story of people thinking about these questions. So just to look at these last two results, I used the word threshold, and clearly this is a natural word, and this is the word that is used for this. I'm not going to write down a definition of chromatic threshold, but I'll tell you that these results tell you that for excluding the triangle, the chromatic threshold is a third. So the chromatic threshold would be defined to be something like the supremum of all alpha, so that there exists triangle-free graphs, there exist H-free graphs of density up to alpha that have arbitrarily large chromatic number. But hopefully this example is enough to give you the idea of the definition. I can play this game for excluding any subgraph I like, not just the triangle. Some chromatic thresholds are very easy to determine. It follows directly from the Edder-Stone theorem. The Edder-Stone theorem says that if you exclude a bipartite graph, you can't have density bigger than 0 and actually be a large graph. So it follows easily that any bipartite graph that you exclude will have chromatic threshold 0. And that's sort of not very interesting in the context of these questions. It just follows from the Edder-Stone theorem, which is simpler. Thomason proved in 2002, and it was published 5 years later, despite it being a 2-page proof, that the 5-cycle has chromatic threshold 0, and that's a non-trivial statement. The fact that 5-cycle free graphs with density away from 0 have bounded chromatic number. And then there is a staggering result that was proved in 2014. This is by, let's see if I can remember, it's Allen, Botcher, Griffiths, Kohayakawa, and Morris. They determined the chromatic threshold for every graph. For excluding any subgraph, I mean. So I've stated a simplified version of their theorem that doesn't actually tell you what it is, but they can tell you for any graph G what the chromatic threshold is for excluding G. Their theorem implies in particular that the chromatic threshold is 1 minus 2 over 2 times the chromatic number of G minus I, and I is 2, 3, or 4. I mean, this is an amazing result, like excluding an arbitrary subgraph and completely identifying this threshold point. So we can do this for matroids, of course. This is a pair of theorems that Jim and I proved last year. We showed that if you look at a triangle-free binary matroid, and so here the density, I'm just going to divide the size of the matroid by 2 to the n. It turns out that problem that you get doing that with graphs just goes away for matroids. So density is just the size of the matroid divided by 2 to the n. If you have a triangle-free binary matroid and it's got density bigger than some constant strictly bigger than a quarter, then you've got bounded critical number. And we have a construction to match that. If you have a constant below a quarter, then you can get arbitrarily large critical number while still being triangle free and above that density. The first result follows from the matroidal regularity lemma, which I'll talk about in a little bit, and the second one is a probabilistic construction. So if we define critical threshold, analogously it's the density level above which you have bounded chromatic number, then this says that the triangle, excluding the triangle, gives you a critical threshold of a quarter. So we can ask all the questions that will answer the graphs about the critical threshold. The geometric Edder-Stone theorem tells you that affine matroids, the moment you exclude one of them, you can't have any positive density while still being large. So any affine matroid you exclude gives you a critical threshold of 0. Analogously to Thomason's result, we proved that the 5-cycle also has critical threshold 0, as does any odd cycle. And again, that used the regularity lemma. And unfortunately, well, I'd like to say we have a theorem to match the beautiful theorem of those 5 authors from the previous slide, but we have a conjecture. Again, I've stated a simplified version of the conjecture. We think we can predict what it is. So I think the conjecture, as we've stated it, which is quite technical, we think it tells you correctly what the threshold is for any fixed matroid. But I've stated a simple version of it that just says it's 1 of 3 values. And again, it's a strikingly similar looking result. I is 2, 3, or 4. And we have some good evidence for this. We know it in many cases, and we know that it's a correct upper bound. We know that our predicted value is a correct upper bound for the threshold in all cases. Okay, so that's all of this. So this slide is a little bit of miscellany. I was at the Canada conference in Saskatoon about a month ago, and really I just was thinking about these questions, and the moment you see a conjecture that lives in this world in graph theory, you can make the analogous conjecture for matroids. So any conjecture on this could be easy. I don't know. I think they're probably interesting to think about. There was a nice talk by a guy at Sassurian. So Arman, Gunderson, and Sassurian, they proved, well, nearly proved a fairly long-standing conjecture about which triangle-free graphs have the most cycles. And it's a complete bipartite graph. I mean, it's what you'd imagine. A balanced complete bipartite graph has the most cycles. I guess it's a bit funny that it has no odd cycles, but it's still, it has the most cycles for all n at least 141. Also, it's known for all n at most 13. And it's conjectured to be true for all n. Presumably it is. So we can make the same conjecture, I can say, among all the rank n triangle-free matroids, which one has the most circuits? And, well, hopefully it's the binary affine geometry. You can also ask this question for flats or cycles and so on, and I imagine the answer would be the same. This next question you can think of as a Ramsey theorem for, sorry, no, an Eder-Stone theorem for hypergraphs. So the Eder-Stone theorem, or the base case of it, says that if I have if I exclude KNN, like some fixed complete bipartite graph as subgraph, then I have vanishingly many edges. I have little o of n squared edges. So if you say that for 3 uniform hypergraphs, you get a statement, and this is really a statement about graphs, but you can interpret it as a statement about hypergraphs if you like. That says if I exclude a complete tripartite graph, then I have vanishingly many triangles. And vanishingly many means little o of n cubed, because that's the number of triangles in the graph. Well, n choose 3 or something. So the analogous conjecture there is I exclude a Bose-Burton geometry. I exclude the Bose-Burton geometry that has lots of triangles in it, which is BB T minus 1, 2, 2. So 2 is the codimension of the flat Euclid. And I conjecture that if you exclude that, then you get vanishingly many triangles, and vanishingly many means 2 to the 2r, which is the number of triangles in a predicted geometry up to a constant. This one's a no-brainer. Sorry, that second theorem is Erdish and Rothschild. The third one's not Erdish co-Rado, it's Erdish, Kleitman, and Rothschild. And I hardly need to say anything. Almost all triangle-free graphs are bipartite, so hopefully almost all triangle-free binary matroids are affine. Maybe I do need a little caveat there. What I mean by almost all here is if you take a binary projective geometry and you take a random subset of its elements and you condition on it being triangle free, then it should be affine with probability 1. I believe that's different from doing something like uniformly at random sampling from all simple rank n matroids. So simple rank n binary triangle free matroids because of isomorphism issues and so on. This is certainly the natural question. Take a random subset of a projective geometry rather than take a random binary matroid. This last theorem, it's an old result that Brooks proved, and it's a natural upper bound on the chromatic number of a graph. It says that it is at most the maximum degree of the graph.
Can I just interrupt? Sorry.
Yeah.
That previously said you believe it's different, but isn't it the same modulator knowledge that almost all binary matroids have trivial automorphism group?
Probably, but you'd need to know that for almost all triangle-free binary matrices.
Oh, I see. I see. Yeah, no,
I mean, I'm not saying it's not the same.
No. I just
yeah.
was wondering.
Yeah.
Yeah, I didn't get why it didn't follow me.
No, I probably believe both conjectures, but I just think the natural one to look at is the random
of course.
subset.
The natural
Is it
one is the
because
legal
that's more
version.
trackable? Or?
No, it's just because it's more closely analogous to the graph problem. I mean, because when you're taking a random graph, you fix the vertex set and you take a random subset of the clique. Right? I mean, when you think about matroids, you think about edges too much, and things get confusing because you've. Yeah, I mean, I don't know. It just seems to me that the very clear natural analog of the graph question is take a random. In the setting we're talking about, like a random graph is a subset of a clique, a random matroid should be a subset of a geometry. I don't have much more justification for that though. Okay, yes, so Brooks' theorem says that the chromatic number of a graph is at most the maximum degree unless the graph is a clique or an odd cycle. And the moment I see clique and odd cycle, you know, my ears prick up, right? These are things that show up in a context analogous to graphs again and again, as hopefully I've convinced you. So here's my silly conjecture, which I made on the walk, was it 2 days ago? Yeah. So okay, first of all, delta means maximum size cocircuit. That's the analog of maximum degree. But the matroids are weird because cocircuits are huge. A cocircuit in a projective geometry has half the size of the matroid itself, whereas a cocircuit in the graph has 1/n times the size of the graph, with the number of edges in the graph. So I think you need a log to make this natural. So this conjecture is true for projective geometries and true for odd cycles. I don't know more than that.
I think that
yeah.
I have a paper on this, 1976, something like that. 78, something like that.
Oh, okay.
I think the result might be there. I think it's actually a theorem rather than a conjecture.
Oh, okay. Well, that would be nice.
I mean, it's too long ago for me to remember,
Yeah.
but certainly I addressed this kind of question, and certainly I did exactly what you were talking about, so I'd be surprised if the result's not there.
Okay, well, it's nice to have one's conjectures proved 40 years in the past. So now I'm going to talk about perfect matroids. Well, first of all, I'll talk about perfect graphs. So an obvious lower bound for the chromatic number of a graph is the clique number. You need that many colors just to color a clique. Now, a graph is perfect if that bound holds with quality, except that's not the interesting property, because one way to get a perfect graph, or one way to get a graph where this bound holds with quality, is take your favorite interesting graph and then just bang a really, really huge clique next to it. So that graph now has chromatic number and clique number equal to the size of your massive clique, and it's not very interesting. So the interesting property is the hereditary one. A graph is perfect if its chromatic number is equal to the clique number for every induced subgraph. So whenever you restrict to a set of vertices, take that subgraph, you get chromatic number equal to clique number. So here's a couple of non-examples. An odd cycle, a 7 cycle for instance, has, well, an odd cycle of length at least 5, has chromatic number 3 and clique number 2. Also, the complement of an odd cycle will have chromatic number ½ plus 1 and clique number ½ minus 1, so it's not perfect as well. And these examples, odd cycles and their complements, are absolutely fundamental for, well, there's 2 well-known theorems about this. The first is the weak perfect graph theorem. This was conjectured a long time ago and then proved by Lavash in '72. And it says that the graph is perfect if and only if its complement is perfect. So the imperfection of one of these graphs follows from the imperfection of the other because they're complements. And then this follows from the strong perfect graph theorem, which of course was proved by Chudnovsky and Seymour in 2002. And this says that a graph is perfect if and only if the graph and its complement do not contain induced odd cycles.
Thomas and Robertson in that?
Sorry, that should be...
Seymour, Thomas, and
Robertson.
Sorry, yes, Thomas and Robertson. Yeah. Yeah, I don't know why I forgot that. Okay. And I guess I need an odd cycle of length at least, of lengths greater than 3. So a hole is an induced odd cycle that's not a triangle. If a graph and its complement both don't have an odd hole, then the graph is perfect. So of course perfect graphs have applications in all sorts of things, including polyhedral theory, and I don't really understand those, but clearly perfect graphs are important. Okay, so I'll talk about perfect matroids. Now, Rutger asked Jim what a perfect matroid is a few weeks ago, and we thought about it for a day or two, and it turned out, talking to James, that James Oxley's student Alan Mills did basically the same stuff that we did in a paper from 1999. But there's some nice questions, and I think that there's just a surprisingly nice thing about perfect matroids if you just define them and go through the motions. So the clique number, what's that going to be? That's going to be the rank of the largest projected geometry restriction. So I'll call that omega. That's like the clique number. And as you would hope, the clique number is a natural, I'm going to keep calling it the clique number even though it's a projected geometry I'm looking at. The clique number is a natural lower bound for the critical number, and that just follows from the definitions. But also, the clique number has a way of viewing it that doesn't work for graphs. If I'm asking the clique number, I'm asking for the biggest projected geometry restriction. If I ask for the critical number, I'm asking for the biggest flat of the ambient space that's disjoint from the matroid. So that's just like asking for the clique number of the complement, up to some obvious subtractions and so on. So the identity that's true is that the clique number of M is the rank of M minus the critical number of the binary projective geometry complement of M. And this doesn't matter how big the ambient geometry is. Again, the appropriate things will cancel each other out. So complement is a sort of pseudo well-defined operation. It's well-defined if you say I'm taking the complement in a spanning geometry, but it doesn't really matter. So what does being perfect mean? It means that the critical number is equal to the clique number for every induced submatroid, and an induced submatroid should be the restriction of the matroid to a flat. And that's like an induced subgraph. So if you just rearrange things, you get matroid's perfect if and only if you have the hereditary property of critical number plus critical number of the complement equals rank. So this is an observation, not a theorem. I mean, a matroid is perfect if and only if its complement is perfect. And that follows directly from the definition. So now you can go and ask, what would a strong perfect matroid theorem be? So you certainly see that odd holes, so non-trivial odd cycles are minimally imperfect. That's still true because they have projective geometry. They have clique number 1 because you can't find even a line inside them, and the critical number is 2. And their complements are imperfect, and that's because of this complementation result. You don't actually even need to work it out. But things get a bit ugly from there. If you just look at the graphic matroids, you find out that a graph is perfect if and only if it's four-colorable and has no odd hole. So being four-colorable is... So the complement of the graphic matroid is not the graphic matroid of the graph complement. It's the binary projective geometry complement of the graphic matroid. So you have to play around with some definitions here. But you actually see this is a fairly straightforward thing to prove once you just do the work. So this gives you a characterization of perfect graphic matroids. And you can ask what's minimally imperfect now. So minimally should be with respect to induced subgraph, or if you like, an induced submatroid. And you see things that are not odd holes, they're not anti-holes. So MK5, actually no, forget that. So MK5 is not an odd hole, it's not an odd anti-hole in the matroidal sense. And it is imperfect because it's not four-colorable, but all its induced submatroids are four-colorable. So this is a counterexample to the most naive formulation of the strong perfect matroid theorem. This is a minimally imperfect object. It's not an odd hole or not an odd anti-hole. So I could make an optimistic conjecture, but I don't know what it would say. So I'll make a pessimistic one, which is that there are infinitely many minimally imperfect matroids that are not odd cycles. I guess I need to say, sorry, odd cycles and odd anti-holes. No, I don't, because they're not even graphic. So even
Peter, a
yeah.
stronger conjecture. I mean, but it's hard to state formally. Then you already have an infinite number of minimally imperfect graphs because you've got odd cycles and they come in a family.
Yes.
So would you can strongly conjecture that you couldn't characterise the minimally imperfect matroids by
you would
well characterised family, or exactly? I'm not sure how to say it.
You would hope so, but we know dozens of them up to 12 vertices. So I mean, there's some work to do, and maybe you're right. but it seems like they're ballooning quite a lot.
So it looks nasty.
Yeah,
exactly.
and we've kind of gone up as far as the computations we've written we're capable of. So it looks like there could be lots of these things. Perhaps Gordon could tell us more if you got interested in this.
Peter,
Yeah.
MK5 is a complement of a 5 cycle?
MK5 Matroid, is it?
Yeah.
Oh, okay. Okay, so that's not actually an example then. So it is minimally imperfect, but it's not interestingly minimally imperfect. But there are examples of things that are. I don't know any off the top of my head, but I have a list of a whole bunch.
Are your other examples graphic or no? Just
Yes, so the examples we know are graphic, and there's plenty of them even in that class, so that's probably interesting enough to look at. Yeah, I mean, it seems like it's, the strong perfect Matroid theorem is probably going to be difficult, big surprise, but it seems to be difficult even in the special subclass of graphic Matroids. Okay, so how much time do I have? A little bit. Okay, so I just wanted to mention some tools briefly. I talked about this in Princeton, but there's a matroidal regularity lemma. So Semereti's regularity lemma is this beautiful structured theorem for all graphs. I think it's from 1970, and it says more or less that every graph admits a partition into a bounded number of sets of vertices, so that most of the bipartite graphs you get by looking at the pairs are somehow pseudo-random bipartite graphs. I won't say anything more than that because I don't want to get on to something else. But it's very useful. It was originally used by Semereti to prove his theorem about arithmetic progressions in the integers in any dense subset of the integers. But it has all sorts of applications. You can derive the Edstone theorem easily from this lemma, for instance. One of the results of this lemma is that if you have a graph with not many triangles, so it's got a little O of n cubed triangles, then you can remove a very small number of edges and become triangle free. And that's something that's hard to prove directly, but it's an easy consequence of the regularity lemma. So it's a very powerful tool if you're looking at subgraphs and things like that. And there's a matroidal version. Ben Green proved a regularity lemma in 2005 that applied to arbitrary, I think, finite abelian groups. And this was a very long paper, but his theorem is absolutely clean and beautiful when you apply it to the group GF2 to the n, which is luckily the one I'm most interested in here. So if you look at a subset of GF2 to the n, aka a binary matroid, it turns out you can get what's called a regular partition of the elements of this matroid that's very, very analogous to the regularity lemma. So it says that I can partition any such matroid into two decayed parts. Now, a regular partition is what you can think of it as a special type of representation. So I'm going to pick some k. So here in this picture it's 3, but you can think of it as some fixed integer. Now, a regular partition is what I get by I'm going to sort the elements of this matroid according to the first k rows. So here there's 8 possible things in the first k rows, and I've partitioned up the columns according to them. The partition is regular if for all but an epsilon fraction of these rectangular submatrices you see here, the submatrix is what I would call epsilon pseudo-random. So epsilon pseudo-random means that so one of these matrices is pseudo-random if the number of columns in a given hyperplane is roughly equal to the number of columns not in a given hyperplane. So it's it behaves like a random set in a certain way. Sorry.
So this says in given binary matrix, I can find some matrix representation.
So there is,
I can pick the representation I want to make this.
So yeah, so there will be a small k, like a k that's bounded by some function of epsilon, so that there exists a representation which looks like this.
Right.
So the content is that most of these things are pseudo-random. So here one of them is not pseudo-random and the rest of them are.
So
But-
you don't choose k, they choose k. Chooses k for you.
But k is bounded. That's the point.
Right,
Yeah.
it's bounded, but it chooses k for you.
And this gives you all sorts of things. So as I said, it proved these things about critical threshold, about triangle free and C5 free matroids. We use this regularity lemma to prove that. And also you get a triangle removal lemma that's exactly analogous to the one for graphs. If you have a binary matroid with vanishingly many triangles, then you can remove a few elements and be triangle free. Anyway, so this regularity limit I think is going to be a very useful tool. I don't quite understand the full power of the definition of pseudo-random. There's lots of things I'd like to know about what you can actually do with this limit. A lot of the stuff with the Vacquerie regularity limit, I don't know how to make it work for Matroids, but if I could, I would be very happy. Okay, finally, this last slide is a crash course in flag algebras. So this looks like gobbledygook, but it's really cool, and even if you haven't followed any of the rest of this talk, I encourage you to look at this. Flag algebras are a calculus of probabilities or densities. So these are used usually for graphs, but here I'm doing it for binary matroids. So I'm going to take a binary matroid, so a subset of a geometry, and I'll think of the points in that thing as green, and the things in its complement as red. And I'm going to use very unorthodox, strange symbols to represent probabilities. So green dot means the probability that a random point is in your set. Side of the set over 2 to the n. Red dot means the probability that it's not. Now, 2 to the n is not quite right, it should be 2 to the n minus 1, but all these lower order terms we're not going to care about. So these are all the equalities in here are up to a little of 1.
Can you just put the 0 vector in? And
Yeah, you could, yeah. It's not going to make a difference. Then I define lines to be probabilities that you get lines of a certain type. So this thing here is the probability that a given line contains 3 points in x, 2 points in x, 1, 0 points in x. So these are numbers between 0 and 1. And there's some nice things we can see. 1 is the same as the probability that points in the set plus probability that's not. It's also the same as when you get 4 types of lines, so the probabilities add to 1. These two statements are encodings in the calculus of basic counting arguments. If I count the number of pairs xl, so x is a point in L, and I divide through by common 2 to the n's everywhere, then I get this statement. The density of a point, probability that a point exists, is equal to the probability of a full line plus 2/3 times the probability of that line plus 1/3 times the probability of that line. These constants here are the probability that you see a point in that particular submatroid. So you see a point with probability 2/3 in here, so you get a 2/3. These are all things that you can just do if you write down the counting arguments. Here, the probability of a point squared, if you count the number of triples x, y, l, so that x and y are both in L, and you ignore lower order terms,
what's L?
L's a line,
Okay.
a line of the geometry. Then you get the square of the probability of a point is the probability of a full line plus 1/3 times the probability of a 2-point line. And the smaller lines don't contribute because they don't contain 2 points. So I'm going to prove an approximate version of the Bose-Burton theorem using this silly terminology. So the Bose-Burton theorem tells you, well, the base case tells you if you've got a triangle-free matroid, then it's got density at most a half. It's got at most a half times 2 to the n elements. So it's triangle-free, so I've said that the probability of a triangle is 0. Now I'm just going to convince you I'm not cheating here. 0 is less than or equal to the square of something, that's fine, which is that, if I remember high school. And then 4 times the probability of a point squared, that thing there is 0, so it's 4 times 1/3 of that. Then I left that the same. Then the probability of a 2-point line, using this to simplify, again that's 0, so I can turn that thing into that. I mean, you can just believe me, I'm not cheating here if you want, but it's all just using these equalities here. And then finally I get 1 minus twice the probability of a point minus 2/3 times the probability of a 1-point line. So 0 is less than or equal to 1 minus 2 green dot minus 2/3 of something positive, so green dot's less than a half. So this, I mean, of course there's not much that's actually non-trivial. This is just basic counting encoded in a weird way. But when you do this for higher rank, you just get this incredibly powerful set of tools where you can use things like semi-definite optimization to work out the right inequalities to make things true. There's been an absolute deluge of results that use flag algebras to resolve old conjectures for graphs in the last 2 or 3 years. So these are really new things for graphs, and I think that there's no reason they can't give us beautiful theorems about binary matroids. Okay, so finally, some pie in the sky ideas about what I'd like to use to prove some of these theorems. When you're looking at triangle free sets, there's some free sets in a group. So, I mean, that's additive combinatorics, and the regularity lemma gives you a certain type of uniformity, which you can think of as bounded Fourier bias, and then there's other more complicated notions of uniformity by Tim Gowers, and I mean, possibly I'd need to understand the regularity lemma and the things associated with it better, but I'm sure these things are relevant. I'd like to know about limit objects for matroids. Dan Crowell gave a beautiful talk in Princeton about limit objects of graphs. I don't know what a limit object for a binary matroid is, and it would be really nice to be able to do analysis to solve some of these problems. So my best guess is that ultra products might work. They're a way of sort of formally turning a sequence of finite objects into a well-defined limit object on which you can do analysis, but again, I don't know how to do that yet in the binary setting. Andrew Thomason gave a nice talk in the ACC MCC in Wellington last year about something called hypergraph containers, which are this sort of black magic technique that you can use with independent sets and hypergraphs. And one of the things that him and Saxton, who was his PhD student, already know how to do with these things is count solutions of systems of binary equations, of linear equations in some vector space and so on. So I think that this really will have some applications for what we're interested in, because a system of solutions living inside some set is basically a restriction, a submatroid. And finally, I mean, we've had some success in just mining the graph techniques when we looked at things like these threshold functions. The graph techniques really inform you. It can be an interesting exercise to figure out what something would actually say for matroids. There are some important differences, but somehow there's a common spirit to these things, and the graph ideas can be quite helpful. Anyway, that's all. Thank you.
Questions?
It's always struck me as odd, these dense triangle free results. Normally, to make the chromatic number go up, you add a few edges. But when you impose triangle free, it suddenly drops down again.
Yeah, I guess it's that it's very hard. I mean, they're just very rare objects, and you have to do silly things to make them, and silly things force the chromatic number down. Yeah, it is counterintuitive. Yeah. I mean, it's even more counterintuitive that it works for arbitrary excluded subgraphs. You still get these thresholds that above which you have to do something silly.
Yes.
Other questions or comments?
So I see that next week at right now at the DCC, somebody's talking about a limit sequence of matroids.
Oh, who's that?
Anita Liebenau, who has Dan Crowell as a co-author.
Oh, okay.
But some work is being done.
Right now.
Shame we can't be in two places at once.
Yeah.
Anyone else?
Yeah. So, in the perfect graph, in perfect graphs and in perfect matroids, you have to get rid of the trivial cases. And you can do that by closing it downwards under subgraphs or under flat restrictions. Can you get rid of those trivialities by imposing some type of connectivity? I'd say it's a round matroid where chromatic number is equal to clique number. Is that then an interesting property?
It could be. My gut says that that's not going to work, and the reason I think that is because back in this world of triangle-free graphs, you had this example where you take a big dense graph and then a small interesting graph that's triangle-free, and you have something that's dense for a boring reason. Now that's disconnected, but if you just connect your small interesting graph to the bipartite graph, it's very easy to do that in a way that adds lots of edges without creating triangles. So connectivity, I think, is a bit of a red herring there, and it's only for that reason that but roundness is very strong, so I don't know. That's a good question. roundness is certainly quite a natural property in the world of matroids of exponential density. Round binary matroids are a very rich class.
What's a round graph?
A clique.
Yeah.
A clique with some parallel edges and loops.
Yeah.
Okay, let's thank Peter again.